So this is part of the Office of Naval Research funded project, Littoral Mudflats and Shorelines, Soil, Sea, Ice, Air, and benthic life interactions. The project aims to develop a fundamental and comprehensive understanding of the geomechanics of littoral mudflats and shorelines towards reliable prediction of geomorphodynamics, trafficability, and navigation from satellite images and geoacoustic surveying. We are really excited to have Dr. Alexandra Schueller here today. She's a postdoctoral researcher at the Center for Applied Coastal Research at the University of Delaware, where her work focuses on nearshore hydrodynamics, coastal resilience, and flood emergency management. She received her PhD from the Technical University in Kaiserslautern, Germany in 2022 with a dissertation on improving flood emergency strategies. And she is actually also just a published book author. I was very excited to have a look at her newest book. So we are very excited to have you here, Alexandra. Please take it away. Welcome.
Okay. Yeah, thank you so much. And yeah, thank you for the kind invitation, Nina. I'm really happy to be part of this series. And the title of today's topic is From Swash Zones to Tidal Flats. And yeah, first, maybe you ask yourself, what have those two areas in common? Yeah, so swash zone, highly dynamic, wave driven, really fast, tidal flats like muddy and slow. So what do they have in common? So both have changing water levels. They have conditions that change rapidly, like for instance for trafficability in the mudflats or with the waves coming and going in the swash zone. And standard methods often fail. So with our sensors in the swash zone, it's not so easy to collect good data in those zones, for instance. And that's exactly why I find those areas so interesting. So my background, I come more from this river and coastal perspective, and I would like to take my experience to the tidal flat. And why tidal flats? Because those areas are so highly dynamic with changing conditions and so highly interdisciplinary, and that makes it very interesting, in my opinion, to dive deeper into this. So today I want to show you how I bring tools from the swash zone and from rivers and the experience from rivers and beaches, and we think them for tidal flat research. So it's highly interdisciplinary, and yes, it's ambitious, but I think that makes it really exciting. So let's dive into the topic. Not working. 1 second. I think I need to click in on it again. So why do tidal flats matter? So tidal flats are often overlooked. Yeah, so they are really muddy. No one really lives in those tidal flats itself. But they are the first to be hit after with a coastal disaster, like for instance hurricanes or tsunamis. So in flat low-lying areas, they are often the only access routes to get to those coastal areas, and the conditions can change rapidly. One day you can walk on it, the next day you can't. Yeah, and there are only limited methods right now to assess if you can walk on it or not, and what are the ground conditions right now. So we need reliable, rapid assessment methods for those systems to save lives and equipment. So let's start with where I'm coming from. So, or we could also name it, what can someone working in the swash zone and with flood and storm impacted areas contribute to tidal flat research? So the first main research area that I have focuses on hydrodynamic processes in the swash and in the surf zone. So I focus on velocities, wet shear stress and turbulence, and as well on munitions migration and burial. My second main research area is about natural hazards in riverine and coastal environments. So it's about real-time monitoring, for instance, for those systems. It's about post-storm reconnaissance and rapid assessment of areas. And it's about flood emergency management and operational management. So let's start with the first main area that I'm working on as a postdoc, the hydrodynamics in the swash and in the surf zone. It's an NSF project together with Queen's University and University of Wisconsin-Madison. And here you can see our latest publication that we had about this project. So the swash zone itself is the upper part of the beach and the land-sea connection. We have here upwash processes going on and backwash processes. And it's a highly dynamic zone. So in nature, waves often approach the beach with an angle. So, and we want to work with this realistic situation, so oblique waves. The question is, how do oblique waves influence alongshore and cross-shore conditions at the beach? And yeah, to get those conditions working, we wanted to look at different velocities. So in 3 dimensions. So we have on the one hand the cross-shore velocities, so to the beach, like this. Then we have alongshore velocities along the beach and velocity profiles of the sea component to look at this as well. And then we focus on velocities and wet shear stress and of course the corresponding water depth. So because we have a lot of different conditions at the beach, in nature everything is really complex, we try to sort out the different conditions. So we thought it's the best to build our own beach in a lab, and Queen's University said, okay, you can have our wave basin to build your own beach. And so we were able to build this rough slope. As you can see here, you can see one of our trials. So this is the beach slope. We have different sensors to investigate velocities and water depth. And we have changing forcing conditions. So we are able to move this huge paddle around in the wave basin, as you can see here in different angles to get this oblique forcing of the waves. We are able to produce different heights of waves with the wave paddle and then send them to the beach. And then we measured everything with a smooth slope, and then we sandblasted the slope and measured everything again. So with each trial, we changed one condition to get an information about the setup. And as you can see, we had different cross-shore positions along the beach to get an information about what happens at this beach, and then at different alongshore positions. So the sensors that we used are shown here on the right side on the slide. They are called Vectrino 2s from Nortec. They are really fancy sensors, so they can measure 3 centimeters in the water column, where you get 30 different information about velocities in the cross-shore and the longshore direction. And with this, you get a lot of information. So the trials were 10 minutes long. Yeah, so you have a lot of data. And to compare those different trials, we needed a statistical method to compare things. So we found out when each wave cycle starts. And so with this, we identified events. And then we used a method that is called ensemble average. And with this, we got an ensemble average wave cycle that represents this wave flow behavior for this one trial. So that makes it easier to compare different conditions and cases with each other. So again, I used the same color schemes, the same colors as before. With X, you see the cross-shore position, and in the swash and in the surf zone, we have something like this wave profile with the cross-shore velocities. You can see here the upwash in this direction. Then we have here the flow reversal where the velocities get negative. And then we have here the backwash processes. So when you stand the next time at the beach, you can really look at those things maybe from a different perspective. As well, we have a longshore velocity, so going along the beach. So the next time when you stand at the beach, look if the waves just go up and down, or if they maybe go a little bit to one side as well. And here you can see that this is normal, that the longshore velocities stay positive. So we have all the time velocities in along the beach. With the Nortec Vectrinos, we are able to plot profiles because we get three-dimensional information. So we can plot the cross shore to the beach and along the beach information over depth, because we have 30 different informations in this water column that we can plot. And then you can see something like this, yeah, where you can see, we call it boundary layer that we have, or here, very nice boundary layer. So we can use this information to see what happens, for instance, when we change the bed roughness. You can also plot it in this way. We call it p-color plot in MATLAB. So it's just the same information as with the profiles, but for each point in this flow cycle, we have a lot of profiles, and we show the height of the velocities with a color. Yeah, and then you can see how the velocities change here in the cross-shore direction and in the along-shore direction over one representative ensemble average flow cycle with the depth and over time. So what happens? And then we can plot as well bed shear stress. Again, blue to the beach, red along the beach. And you can see that we have two big peaks representative here for the cross-shore shear stress, bed shear stress, here at the beginning of the flow cycle and at the end of the flow cycle, and the longshore velocities stay more positive all the time. And then you can see here that the longshore bed shear stress dominates over a specific part in the flow cycle. And this is why we say it's important to include the longshore component as well in models and future experiments and everything. So this is just a short overview, quick overview of what we are doing. And my second research area is about munitions migration. So it just started. I have no results right now to present, but here you can see the munitions here. So they are really huge. Someone asked, I think Stephen asked, who was it? Someone, yeah, you asked about what the munitions look like. So here you can see them. They are really huge. So we have 6 of them. We pour them out at the beach in 6 different cross-shore positions along the beach. So we do beach surveys, look at the bathymetry, and we go out every 6 to 8 weeks to just track the munitions where they are with the divers. The second main research area is about natural hazards. So my doctoral thesis was about flood emergency management, and that includes optimizing processes across 3 phases. So before a disaster happens, we have this typical preparedness for a disaster. Then when the disaster happens or happened, we have the response. And then after that, this long-term process of recovery. Here you can see one example of the flood in the R Valley, where we had all those processes really in a short cycle, and now they are still in the recovery process, and that happened in 2021. So during my doctoral thesis, I focused on different scenarios to have a structured way to look at things and to optimize things. So it was focused on rivers, and then I looked at different catchment sizes, flood intensities, or structure failures, or combination of events. And how can we use our hydraulic engineering thinking to bring that into disaster management to improve processes, yeah, for those different scenarios. And I would like to focus now on this preparedness aspect, because I think that is something that would be interesting for the tidal flat research as well. And the goal is, yeah, in general, to support better decision making through data strategies, clear thresholds, and realistic preparation times. So in this word with timing is really important in the when you look at preparedness. So the question is, can we act before it's too late? And I worked in the R Valley after this huge flood disaster that happened in Germany, and yes, there it was too late. So they had only 24 hours to react after the information the flood is coming, and the flood actually happened. Yeah? So we call this prevention time. From recognizing a disaster is coming to the disaster is happening, we call that prevention time. Additionally, there's this other time called preparation time. So it's the time that you need to get measures ready, like building dams, evacuating people or something. And this relationship between those two times is really important. Yeah? So in general, for operational things that you do. So in the positive case, the prevention time is greater than the preparation time. In the negative case, as we had in the R Valley, there was not enough time. So the prevention time was smaller than the preparation time. And yeah, there was only reaction possible. That was the only thing. We call it reaction. So what can we do? So we can do different things, like for instance, earlier detection. And I think that's an important part where we as researchers really can work on, like including triggers and thresholds and bringing them to people in operational management or disaster management. And with recognizing disasters earlier, you extend the prevention time and of course the preparation time, so people have more time to think about things. As well, organizational process optimization, yeah, that they understand our language as scientists, for instance, that we work with them together to build those triggers and thresholds, to bring them into their plans, or to work with them at the beginning together, something like this, to create something like dashboards where we work with them together, where they can collaborate, that we speak one language. So the best thing is to combine those different things, like those solutions in one thing. And in my opinion, triggers and thresholds is the thing where we as researchers can really help to improve things. And this is where I'm really engaged in doing this in Delaware. So we have there a real-time monitoring to improve coastal resilience. So we bring out water level sensors and wave buoys along Delaware's coast and bay. So we have 7 wave buoys and several water level sensors. So I work together with the communities, do a lot of outreach, and we want to collaborate with the emergency managers and want to bring it into our research as well. Yeah, so to improve our models. And it's the same for tidal flats. I think it's good to have this real-time data to get a feedback out of the flat in a remote way, and to use that to make clear decisions. Then about post-storm rapid assessment, that is the third part. During that near-gear data campaigns, we worked after Hurricanes Helene and Milton. So when a hurricane gets over this area, it impacts the water and the soil or the land. Yeah, so you need a seamless picture from the water to the land. You need that big picture from the air, but you also need to look in the soil because the coastal processes also, we see something maybe with the DCP or something. So, and that is also relevant for tidal flat research, yeah, capturing fast changing conditions like we do in that rapid assessment, but also fast changing conditions in tidal flats. Maybe you can reuse those instruments and use it, apply it for both questions. So we surveyed 3 key locations along Florida's Gulf Coast. We had Cedar Key with Suwannee, then we had Horseshoe Beach, and then additionally the area around Venice Beach with Midnight Pass, Milton Pass. We did 2 pre- and 2 post-storm surveys around Hurricanes Helene and Milton, and we had LiDAR measurements, remote sensing methods, hydraulic surveys, geotechnical surveys. So a lot of methods that you can also apply to the tidal flats, yeah, and to figure out which methods work very well together that fill in this gap to give us the big picture. I would like to focus now a little bit on a geotechnical survey. So after Hurricane Helene and Milton were done, we went into the field, and I was part of the team that measured with a dynamic cone penetrometer called DCP. So we use the Panda DCP. It's a portable instrument cone penetrometer, and it provides dynamic cone tip resistance called QD. And it has been used effectively already in challenging environments. It was used for post-blast liquefaction zones, intertidal beaches, and with results comparable to a CPT. So here's one example that I would like to show. We called it a tidal flat or mud flat. It was close to a tidal flat, but yeah. So those are preliminary results from Cedar Key. So you can see here this red arrow. It's not working, the pointer. But yeah, when we saw in Cedar Key, we had here, now you see 3 different locations in a cross-shore profile, with black the most landward and yellow the most close to the water. Here you see preliminary results. So you see on the x-axis QD, and on the y-axis you see the depth. Here you see one example of this DCP profile. So when we go now closer to the water, what happens with the DCP profiles? You can see not much is happening. Yeah? So that is the result. So we have really a soft soil at those data collections points in the cross-shore profile, but we can see that here we went a little bit deeper into the ground and we hit a layer of shells, mussels or something. I'm curious if we would see that as well here, maybe at those 2 other points as well. Additionally, we collected some data closer to the houses, so 3 points relatively close together, as you can see here in this box. And we had here, we hit a root, so that was not working very well with the red line. With the other 2, we were able to get deeper into the soil, and we hit a more stiffer layer around 0.8 meters. That could be because of the trees around that we had, maybe because of human activities when they built the houses, that they had heavy machines on the ground. So we need to interpret those results. So we need to see what the DCP is telling us and how we can use that, apply it for tidal flat research, for post-storm reconnaissance in the future and something. But I think this instrument has a great potential, and we need to see how we can translate soil stiffness into values for decisions in the future. And this moment sparked a lot of research ideas that I will show you next. So what I have done, so I worked in this post-disaster reconnaissance, so rapid assessment of areas using triggers and thresholds, measuring velocities, bed shear stress and turbulence, then looking at this operational aspect with the flood emergency management, and as well about migration, burial, and tracking of things on the seafloor. And this is what I bring to the flat. This is what I actually would like to apply. And those are not disconnected studies. They build a story that we can use for tidal flats. Yeah. So, for instance, handling dynamic systems or measuring under difficult conditions, using real-time data and rapid assessment tools, and as well combining disciplines to get the big picture. So now I would like to explore or would like to show you what we can use and bring to the flat, and all those ideas are grounded on the methods that I just shown. So in general, for tidal flats, we need a really multidisciplinary approach. So where different teams come together, bring their expertise into the field, and then to combine it and to see how we can fill in gaps. So we have geotechnics and sediment mechanics. We have biology and in-fauna sediment interactions. We have hydrodynamics and sediment transport. Then remote sensing and geoacoustics, and on the other hand, geochemistry. And all those have to build the big picture. And now I would like to show you some ideas that I have that fit into this big picture and help to get new information. So the first one is about rapid in situ assessment using geotechnical methods. So I would like to combine in the future in situ methods for rapid assessment, like combining DCP methods with the blue drop from NINA, because the blue drop is a very nice instrument that shows how rapid assessment could work. It's easy handleable, portable, and it's useful for different environments like muddy areas, but you can also apply it on the beach. Yeah? So the thing is that the blue drop can only penetrate the first layers of the surface, like in muddy environments, something like up to a depth of 1 meter. The DCP can go down to a depth of 4 meters, can maybe fill in this depth idea, so the information. And it's also a very portable method. It's a lightweight that you can use. You have the hammer that you use. And yeah, but it's more, I would say, for not so really wet areas. So it gets complex when you get out of the land, I would say, where the blue top is still working very well. We need to maybe improve this method a little bit in the future. So the question would be, can a combination of rapid in situ tools like DCP and blue drop improve trafficability prediction for logistics planning in dynamic muddy environments to get to a standardized tool for rapid assessment, maybe with combining 2 methods or something that you can really use in difficult to deploy areas. So the question with the combination of those methods is, can we see the pattern from the high to the low tidal flat? So we weren't able to see that in that rapid assessment after the storm. But what is in a real tidal flat? Can we maybe see some special patterns? When we repeat cross-shore deployments at different alongshore positions, can we see something, or was it just there at this one position? And is it really just 1 point information, or can we get out of this a big picture, like an aerial information, when we combine it, for instance, with other methods? The second thing is the timing. As I said, timing is always very important in disaster management as well as here in tidal flats. Yeah, so we have those changing conditions. We could do the measurements during mean water level and then later during low tide, and to see how does the tidal stage affect DCP readings in the tidal flat. Is this maybe a very important information when we want to collect or create an alert system or warning system? Do we need to add the tidal stage to it? Does it affect trafficability in a which way? And it's all about go or no go decisions for the operational managers later. Then, of course, about the season, because with the season we have changes. We have maybe heavier rainfall seasons, or we have freeze and thaw cycles that influence the soil characteristics and everything. So do we see a difference for the DCP measurements and combination of DCP and blue drop when we change it over the time for different seasons? And then, can biological activity influence DCP results? So I know, Nina, that you did measurements with blue drop and worms together. If you can see a difference, the question is, when you go now deeper into the soil, can you see something as well? And as well, is there a difference between vegetated zones and unvegetated zones? Is it really useful in those zones, or is maybe one of the instruments not really useful when you have a lot of worms in the ground, for instance? Then, of course, looking at different climate zones, because only when it works in Florida, there's no, we don't know if you can say the same for when they want to make a military operation in, I don't know, New Hampshire, and maybe we have completely different conditions there. Yeah, so to get really a result out of it and to create something like an alarm warning system, you need to apply it to different environments and climate zones. And here comes now my perspective that I have from this operational management, flood emergency management. It's always so important to translate what you do and your knowledge into operational knowledge. So I can't explain to an emergency manager or someone that never studied something in the engineering field about QD or show QD profiles. They would say, what shall I do with that? Yeah? So they need a clear information like go or no go, or you can walk on it, you can drive on it with a truck, or you can drive on it with a car. That is useful information that those people need, really short information that they can work with. And then maybe to get out of the DCP something like the bearing capacity. Yeah. and maybe to add to those deep 1-point profiles another value or a coefficient or soil profiles or something else from a classification system to get aerial information that we can use. The second thing I would like to talk about is about hydrodynamics. So nearbed hydrodynamics. This is the field where I'm coming from, where my postdoc is about. So there were some studies in tidal flats doing hydrodynamic research. For instance, Peterson with Jack Poleo, they did some research in the tidal flat in a very shallow channel in Delaware, where they used Vectrino tubes. Everyone else would say, are you crazy? Vectrino tubes, they are so sensitive. They can get destroyed so easily. But they did it, yeah, and they got results out of it, yeah, and so they were able to get velocity profiles out of it. The problem is that in the tidal flat, it's moving so slow, the boundary layer is much bigger than in the swash zone, yeah, so in general, you need sensors at different heights above the bed to resolve the boundary layer. There was another study, for instance, from the USGS team, and they used ADVs, for instance, in the field, and combined them with different other sensors like pressure sensors or optical backscatter sensors and brought them out in the field. So there are ideas that we could use and to work on, and my idea would be to create something like also a rapid assessment tool, yeah, that you can bring out really easily in the field, maybe without 10,000 of cables or something, yeah. So because we have muddy red areas, laptops, cables, not so easy. You need to get it in the field. So the goal would be to get nearbed velocities in X, Y, and Z direction. We could get this with Nortec vectors, for instance. Then to get bed shear stress using the quadratic thread law, because we have only 1-point information. Then to calculate turbulence, get information about flow directionality in the mudflat, and then what changes when we have ebbs or tides. And things to consider is that those ADVs, they need 14 centimeters difference from the bed. Sometimes they try to connect with each other and disturb each other, so you need to get them out of the way of each other to install them, to avoid disruption. And yeah, field ADVs are also a little bit larger and bulkier, so when you want to deploy them on one tripod, yeah, you need to see how you can do it. Yeah. And then also the question, do you use aluminum, do you use PVC, PVC or stainless steel, for instance, yeah? Of course, all the time combined with an RBR, so a pressure sensor to get information about the water levels there. About rapid assessment, I saw something in your lab as well, Nina. So using the Aquadop, for instance, yeah. So he reported out up looking, but I think it would be nice to install it down looking to get the profiles. Of course, we don't have this high frequency that we have with the ADVs, but yeah, it's a really easy deployable method that we could try, maybe try different methods, how we can resolve the boundary layer and get bed shear stress. So all TBD at the beginning. And of course, we can apply those DCP questions as well to the hydrodynamics. Yeah. So what is the influence when we measure high biological active areas? Do the worms maybe create other bed roughness? Yeah. So how does that impact the hydrodynamics? Then when we have vegetated or unvegetated zones or different tidal stages, different climate zones. Yeah. And then the question is that effort worth it? So does it really add something to that classification system, or is it just nice to have a nice research? But now I think it's important to find something out that helps for that classification big picture thing. Okay. The next approach or thing that I would like to add is about emergency management. So as I said, they are the first to be hit after a natural disaster that is coming from the coast. So for instance, hurricanes or storm surge hit the tidal flats, we have sediment overwash, erosion, loss of access, and unpredictable softness at those points. And yeah, the conditions after that change rapidly. The same with tidal flats and tsunamis. So we have those huge waves coming. We have major morphological reshaping of those areas. Sometimes the communities get cut off. So you are not able to come from landward to some communities. And after that, you would need to get in from the tidal flat to rescue people after those events. So they get cut off escape routes. Other thing, earthquakes that happen, yeah. So also disaster that can impact coastal zones. So what happens to the tidal flat after that? Yeah, we have a sudden strength loss in soil, collapse of firm surfaces. What shall we do? So I can't resolve that right now, yeah, because first I think we need that classification system. First, we need a lot of data. We need to understand tidal flats itself for an unimpacted stage. And then later, when we have enough understanding, then we can move on and think about how disasters change those areas and how can we apply this understanding to improve organizational things like preparedness, response, and recovery, and then focusing on those different natural hazards because every hazard has a different impact on those tidal flats. And this idea fits well into the point of surface marker. So it's again about operational improvement, using something like triggers and thresholds, creating alarm warning systems, using something remote sensing and a remote sensing approach from the field and to look at it from the computer. So something like a predictive system. So the problem right now is that we have no real-time visibility into trafficability in tidal mudflats, and it's very dangerous. So you can't send out a team for an operation or to rescue other people when you don't know what the conditions are. So because of that, we need something remote. And it was the same when I worked in the crisis team. There is no time. Yeah, so you need to make decisions right now. And you also need that your people are safe. Yeah, so you need to make decisions without getting more people that die because of your decisions. And this is why these assessment tools are so important, yeah, to get this no, go, and go decisions. So what we need is access corridors. We need landing spots that we can define in tidal flats. And those are right now still operational challenges. Like the decision makers must know where can they land, where can vehicles cross or persons cross, where are soft zones that will trap personnel. Yeah? So to get really information about this area. The idea would be to do something like a systematic evaluation of different surface markers, so different types, different structures, different materials of surface markers for remote trafficability assessment in tidal flats. To identify access corridors and to identify and assess access corridors, excuse me. And then to identify landing spots in those areas. So what we could do is, for instance, use huge metallic crosses, maybe really lightweight, like out of aluminium or something. Try different methods, different materials that you can see from the satellite, yeah, for SAR, or for instance, geotextile patches that you can use for optical imagery. Again, with the goal to get something translated for the decision makers, like is the position of the cross unchanged, then maybe it's accessible, yeah, or there's a high chance that it's accessible. Is it displaced or distorted? Then it would be questionable. So be really careful, or fully covered, stay out of that place. Yeah? I think it would be something that would need to be added to other methods, but maybe with the idea that later we could get rid of the markers and just use the satellite images itself, but that it's additional information that you can use when you build a method. So questions would be, can surface markers provide actionable trafficability feedback for operational mobility decisions when we use SAR or optical satellite imagery? And then about the effectiveness. So which materials, with which structures and shapes, geometries remain detectable? Then about stability, how do burial deformation, and sedimentation influence the visibility? And then, of course, environmental impact, because we bring something in the tidal flats. Yeah, so are those structures sustainable, biodegradable, or can we remove them easily, or will they get stuck in the tidal flat and stay there forever? Yeah, so those are also important things to consider. So preparedness is really important, and as well tactical risk mitigation in tidal flats. And it's so important. You have so much knowledge about tidal flats. They need to get to the decision makers that work in tidal flats, yeah, so that they can understand your research in a way that is easily translatable. So it's important to identify thresholds using real-time data. And then, for instance, to combine tidal flat classification with remote sensing, and then in situ real-time data for those specific points, and then to get the big picture and to get something like a real-time trafficability alert and decision dashboard to go. And before a mission happens, or before a disaster happens, identify corridors, so areas where you want to focus on. Yeah, and then the idea is to optimize tactical planning and decision-making processes for operations in tidal flats. So now I'm at the end, and yeah, so the conclusion is tidal flats are really complex. They are unfortunately still a little bit overlooked, and they are operationally really critical and could be a trap for persons or equipment. So we need a multidisciplinary approach to solve those problems. We need smarter tools, and of course we need more data. This is why we are here, and this is why we are researchers. Yeah? So it's also really important to translate our science into action later. And now I would like to end my talk with a visual metaphor. So showing those 3D classes. Yeah, so the 3D classes have different colors and different angles. And when you look only through one class, you see something, but you don't get the depth of it. So you need to add the other lens as well to get the big picture. And it's the same in the tidal flat research. So you need this multidisciplinary approach to get to solve this problem and to understand trafficability in the complex environments. And yeah, this is why I think it's really important to turn technical measurements into operational knowledge. And with that, I'm at the end of my presentation. And yeah, so include everything that's important. And I thank you for your attention. And yeah, if you would like to stay in contact, this is my email address as well. Here's my latest publication about swash zone research. Here on my website, you find a little bit more information about my research, so all my projects. And here again, if you're interested in the hurricane data set with Nina's exceptional leadership, so you can download it here. So thank you for your attention.
Thank you so much for this great presentation. And so with that, we want to open it up to the question round. And so similarly as last time, I would suggest that we are starting here in the room. And so people online, if you guys have questions, you have two options. So either put it in the chat and Sherilyn will monitor the chat, or lift your hand. There's a hand raising tool, right? And we will call upon you, and then you can unmute yourself and speak. So let's get started here in the room. Leah, go ahead. First hand up.
You showed DCP measurements that had a 0 meter sign. Is the 0 meter the sediment surface, or is that elevation?
That is good question. I think that is sediment surface from the DCP.
From the PANDAS measurement?
Yeah, so that's the standard. So that is just a translated raw information. Here you can see it. So that is where we received the first result. So I think the panda starts when it gets the first information that it has some contact. Of course, sometimes I recognize that the panda gets a little bit into the soil, like 1 centimeter or something, and then you get into the soil. Yeah. So that is just plotting the results, to be honest. Nina.
I think the base platform, you have to remember you put that little box on the ground. So I think the box zeroes it. So I think it's in relationship to that box. So that would mean if you're on grass or soil is hovering, then you would have an offset. But otherwise, I think it's actually soil air interface.
Yeah.
So if you would want to identify layers, would it make sense to basically zero it based on the water?
Yeah, for instance, yeah, I think that would be an idea. Yeah. And as I said, the layers would be interesting, and then as well to create something like to translate it into the bearing capacity, or maybe adding something like an empirical factor or whatever to the DCP to get more information out of it. But this is TBD. So I thought about this on the airplane, and so something we all can think about.
Yeah, thanks. Thank you for this very nice presentation. On this slide, so I have some context. How do these DCP values compare with, say, dry beach sand or something? This is a finer grain material, but of course you got those electrostatic forces holding the sediments together when you get into the clays. Just because I don't know, like what are you up to 10, 20 megapascals with beach sand?
Yeah, so we saw a trend. I would say the cross-shore profiles at the beaches were more interesting, I would say, also for publication. So you really see that the soil gets stiffer when you get closer to the water because of those, I think, the waves under flow conditions that really bring the sand together. So but I don't know the values right now. So we are writing right now a technical paper, but it's all preliminary results, and we just started to think about what the DCP is telling us and how we can use those informations for the future.
Yeah, because it's marked in that left panel that within 1.5 meters in a couple of those profiles, you're jumping up, in order of magnitude in the values. I mean, goes from 1s and 2s to almost 20. So I'm sure that's.
You mean here or what?
Yeah,
this one. This
no,
is
not the red one. The yellow and blue ones.
Yeah.
Down at the bottom, and you're getting up 20 compared to 2 megapascals. That's noteworthy, I'd say.
Yeah, so here I think we had some roots also there in this area. So not the big ones. So we were still able to get with the DCP through it, but it was close to 2 trees where we hit it in the ground. So I'm sure that this is influenced by the trees as well. So I'm not sure if heavy machines could go there, and it's directions where so Stephen, you collected that as well. So I think that's maybe caused by the roots, but yes.
It's next to the houses, right?
Yeah.
I also need that was actually being used to create a base for the houses. Do we want to call on Joey?
Sure.
Joey, do you want to ask your question?
Yes, sure. Yeah. First of all, thank you, Alex. That's a very nice presentation, and thank you for thinking proactively as how you could contribute to this project. I know you probably have, not researched on the trafficability, even though your project, the swashing zone, is very closely related to this project here. I think you touched a little bit about the DCP And CPT, right? You know, I think in this project we were thinking of CPT as a geotech. You know, I think we really like CPT. Can you elaborate a little bit? You know, the difference. I mean, for folks in the audience, you know, including me, I'm not that familiar with DCP, but I'm very familiar with CPT. Which one would it be better, I guess, you know, or should we do both, you know, for in situ testing, you know, to figure out the traffic, to help with the trafficability?
Yeah. Yeah, I know that you thought more of using a CPT in the experiment. Yeah. So I talked with Charlie this morning about it, and we looked at the different CPTs have. So I had a different one in mind because the one that we have in Delaware is really a heavy one. But there are different ones, and the ones that you would like to use is maybe better than the DCP. I don't know. Yeah, so I think for getting the bearing capacity later and to get those depth measurements, the CPT is also very good. And it's more about going deep into the soil and getting this information. And this is why I said that we need to figure out different methods and which one really gives the best information about it. That is true, yeah. So this morning I also thought about CPT, but yeah. So CPT, I would say, is the standard method that a lot of people use. But why shouldn't we give the DCP Panda a chance to maybe show that it's good? I don't know. So I just would like to try it and see if that instrument can be used or not. So and then if it's not working, we can get rid of it and use the CPT. Yeah, that's true. But we don't need the cables, you know. So with the DCP, it's just the hammer and the box. So yeah, both measurements have their pros and cons. So yeah, it's more about seeing what can be good combination with the blue drop than later. But yeah, with the focus more on getting later the classification for the excess classes. Yeah.
Thank you. Thank you.
There's a question from Michael Bennett in the chat. I don't know if he wants to unmute, or I can read it.
Maybe.
Yeah, I'll read it. This is from Michael Bennett. Are there past amphibious operations from which there may be useful data on expected versus observed bearing capacities for vehicles? Two that come to mind are Incheon, South Korea in 1950 and Grenada in 1983.
Okay, could you repeat the beginning?
Are there any past amphibious operations from which there may be useful data on expected versus observed bearing capacities for vehicles?
Yeah, I thought about this as well. I'm sure that there are military informations about amphibious vehicles. Because I think for that project we would need a lot of knowledge from the military aspect. We just talked about those heavy machines that you use in the war. Yeah, could you use those mats, for instance, to walk on it or to transport the materials, like the huge CPT into the tidal flat or something? Yeah, so I think there's a lot that we can learn from military operations that worked for hundreds of years, where no one had a CPT or something else to assess the areas. Yeah, so but still they were able to get into areas. And, yeah.
Any other questions?
She said, great talk,
Okay.
thanks.
Thank you.
Any other questions?
For the DCP data that we collected out in Cedar Key, how comparable was it to different sites still within the Cedar Key area?
Yeah, so I would say the beach areas were really comparable. So with seeing that cross-shore profile, the mudflat was a little bit, so I would say outside, like with that one cross-shore profile here, you saw nothing, in the cross-shore direction. So 1 point would be good as well. But yeah, so we also need to compare it to Midnight Pass, where we have more those hydromorphological changes with the breaches, because that brings in another aspect as well. Yeah, so Cedar Key was highly influenced by human activities. Yeah, and the breaches were more uninfluenced by human activities. So to see that and compare the data as well. But yeah, we are still writing the report, working on it. So I hope we will get a big picture soon.
Okay, any other questions? Still have a few minutes. Go ahead, Sarah.
So like the drop penetrometer, so it kind of, as we have like work with it, goes from a few centimeters to about like a meter, and DCP kind of goes up to like 2.5 meters. So like, how do you envision, like, combining the results from the penetrometer and the DCP in the
Yeah.
future?
Yeah, so I think we can't compare them one to one. So we need to first calculate it into the same unit, yeah. And then after that, compare it. Then we can compare the profiles, because I know it can't be translated one to one. That is true. But I think still it can show trends. Yeah, so the one more for the surface, the other one going deeper into the ground. And really the DCP starts nearly where the blue drop ends, I would say. So it's very good to combine it together.
I guess mine kind of is in tandem to Sarav's question, but it is really interesting, the idea of combining the blue drop data and comparing it to the DCP. Is that something you'd want to try and do with like that phase 3 of the
Yeah.
research collection?
Yeah, that is what I really would like to try. And I also would like to get the DCP a little bit more in the water. So getting more information from the swash zone
Okay.
as well, because we stopped, yeah, I would say 0.5 meters before the uprush line happened. So because we wanted to keep the instrument safe, but building something that we can use to hammer it in the swash zone in the ground would be interesting, just to try.
Mhm.
Yeah,
Mhm.
but yeah, I would like to use this third data collection to really see, for instance, for the DCP, can we repeat the results? Because that is, in my opinion, also important, and what changes. And then with the blue drop, now really focusing on, can we combine those methods? Because now we applied the methods now all 2 times. So we have more an understanding and saw the data first. Now we can do a deep dive into the things again with another perspective, I would say.
Mhm.
Are there other non-contacting tools that people are using, like ground penetrating radar, to kind of measure profiles,
Yeah.
hardness?
Do you mean for velocities or?
Just for, qualitative or quantitative measurement of the ability to hold loads.
Do you mean when you go into the soil or?
I was just
For
thinking
which
about
area?
remote methods, like using ground penetrating radar on a drone to measure, for instance,
Yeah.
Consolidation or, that kind of thing.
Yeah. To be honest, I can't answer that question. Sorry, I don't know.
I think there's some precedence to that. People use that for measuring water depth, for instance, and also, profiling hardness as a function of depth.
Mhm.
So,
Do you mean more the geoacoustics?
I'm not super familiar with it, but I've read a little bit about
Okay,
it, kind of
okay.
comparing some of the things we're doing with sonar and with,
Mhm.
other things.
Yeah.
I'm just wondering if somebody has experience with that.
Yeah. Yeah, so when I worked in Nina's team with the rapids storm reconnaissance, I learned about a lot of new methods. Or just today, when I went with Charlie into the lab, I saw a lot of new instruments I've never heard about. But to combine those things, that is really interesting. And first to get the idea to buy them, yeah, and have the money for that, that's another thing. Yeah, but it's really interesting to answer different questions. And for instance, that panda was never used in the coastal area. And then Jonathan Hoopla had the idea to use that panda in the coastal area. Yeah, so to transfer something that is maybe used somewhere completely different in a different area. And yeah, or like your drones, yeah, with combining it with little vessels, yeah. So this is what we need.
Yeah, it seems like it would be great value added. I mean, not in place of some of the penetration tests, but like Peter's saying, bring all the evidence you have to bear.
Yeah.
GPR would be great because then you get a sense of how it's structured.
Mm.
And if you have an analog somewhere else where you can say, okay, this is giving that acoustic impedance contrast.
Mm.
That's that
And
down
it
there.
allows you for like, to get out to the tidal flats without actually training on it.
Yeah.
Get out there, so you don't disturb it. You're out there, it's safe, not endangering anybody.
Mm. That is good. Yeah.
Great. Any last question? Okay, Noah, go ahead.
Yeah, so in the, so like the go section where you're talking about remote sensing
Yeah.
and doing stuff like that, it seems like the idea of maybe having like a metallic cross like that kind of requires pre-thought of which tidal flats to look at. So maybe if like you don't know where necessarily the flooding is going to occur, like how would you go about that from a remote sensing angle? Could you maybe like look at different features on the mud flat to tell what's moving in terms of that like movement and just optical vision? Like how would you go about that?
Mm. Do you mean to get, because you said about water levels, to get information when it's covered with water, or where to put the crosses?
Well, so like if you were going to have flooding on a tidal flat, but you didn't know to pre-put like a cross there, like how would you be able to tell?
Yeah.
Is that what the idea was purely with water level, or was that sediment movement? I wasn't exactly
It was
sure.
about sediment movement, so more like will it sink into the ground, the
Right.
cross? So to get this information, can I walk on it?
Right.
So of course, sometimes when you have water that covers the surface, you have problems with some remote sensing methods to get an information. So when the cross is covered with water, maybe not so useful, yeah.
Right.
But yeah, for this, really try when it's dry, then to get the pictures and then to see if it's covered or not.
Great. Thanks everyone for asking questions, and thanks so much for your presentation and taking our questions. And that concludes our seminar today. And so I believe we have another presentation next week. So stay tuned for another flyer and invitation. Thanks, everyone.